Okay, everyone, so it's time to begin. And today we're going to cover chapter 16 on the chi-square distribution, two types of chi-square tests, and hopefully get to chapter 17, which is a very short chapter. So your homework 9 is posted, and it's on chapters 16 and 17. And even if we don't get to 17, you'll be able to answer the questions on 17 because we've talked about them a lot before, but we'll try to get to 17. Okay, so reminder that the Exam 1 conflict sign-up is due tomorrow. So be sure to sign up for that if you want to take the conflict. All right, and I'll be sending you this weekend a list of formulas that you need to know for the exam. It's a pretty simple list, and I'll send you an email about that probably tomorrow. And as I said before, you're not going to have a formula sheet. So the only test statistic that we're going to provide for you is the chi-square test stat, which we're going to go over today. You'll still know how to you'll need to know how to do the chi-square test, but we'll provide that test stat for you. All the rest you're going to have to know. Okay, so now let's go to the document camera and go over this chi-square test. Now, so the chi-square, whoops, that's a chi, Greek letter chi squared, goodness of fit test. We're going to do two tests. One is a goodness of fit, we'll do that first, and the other is an independence test. Now, the chi-square goodness of fit tests are used to determine whether your observed data fit a specified model, whether the observed fits an expected model. When the model has actually two or more categories. Remember, with two categories, a 0-1 box, we can use a z-test. What do I mean? This is chi-square is for categorical data. Categorical data. So we've done a z-test where we had two categories. We might have yes and no. Like maybe your answers to some survey, yes and no. And we coded the yeses as ones and the no's as zeros. And when we did that, we did this one sample z-test. That's what we've done so far, the one sample z-test, where the null would have been the observed percent minus some expected percent, right? Some claim that we think it's only going to be maybe 50% heads we see, but we see more than that. And we code it as 1 and 0. So we might do a test to see whether a coin is fair, and we have two categories, or whether, you know, some percentage that we expect in the population, and we get something different in our sample. Okay? So that is, and we had this z, right? We said the observed minus the expected. In this case, it would be percents minus the expected percent over some standard error for percent. That was our statistic. But now, and then we can do a one sample z-test, but we could also do a very simple chi-square test. But what if we have three categories? More than two. So you use a chi-square test. You must use a chi-square test when you're interested in the percent composition of the box that has more than two categories. Then you have to, you can't do this. You can't boil it down to ones and zeros. Watch, why couldn't you? Because let's say you have three categories or more. Let's say we have yes, no, and maybe, or unsure. Lots of times on surveys, they have three categories. And we want to include all three of them, yes, no, and maybe. Well, then we can't, you can't do this, the observed minus the expected, because if you say, let's say you expect 20% or 40% yeses, that doesn't tell you how many no's and maybes you'd expect. You can't boil it, you know, Here, if you say you expect 70% yeses, you know it's 30% no's. So you only have one independent category, right? Because this one's determined by dependence. You only have one, but if you have more than one independent category, like here we have two. If you know the percentage of yes and no's in the model that you expect, well, then this one's determined. But now we can't, these ones and zeros aren't really numbers, they're labels. They're yes or no. We have yes or no for 3 categories. So we basically have 1, 0, 1, 0, and 1, 0, right? So you must use a chi-square test. Why? Why do you have to use it? Because you can't describe what do we always want to do in all these tests? We want to describe the differences between what you observe and what you expect. And you can't describe the difference between the observed, can't describe the difference between what you observe in your data and what you'd expect in your model with a single number like this. Right? You're going to have a whole pattern of differences. And some might be positive and some might be negative. And you need some way to describe them. You can't just take the average because the positives and negatives would cancel out. So what do we do? So what we're going to do is use this statistic here where we take the sum. It looks like, here, let's just, so what do? You take the sum of your observed minus your expected squared. So that's what we do. So we add up the squares of each difference. That's what we're doing. So it's going to be, that's what we're going to do. So we're not going to say observed minus expected over some standard error. What we're going to do is we're going to have, you know, for each category, we're going to have an observed minus an expected. Some may be positive and some may be negative, and we have to square them. And for each one, we basically normalize it by dividing by its standard error squared. That's what this is. It doesn't look like it, but it really is. So what you have, really, the chi-square statistic is really the sum of z-squareds. That's exactly what it is. So now, in this case, you just have one z, right? So in this case, the chi-squared would just be equal to a z-squared. So here you could do a one sample z-test or a chi-squared goodness of fit test, and you'll get the same thing. You'll just get the square of your statistic. You'll get the same value. We'll look at that more later. Okay? But here, when you have more than 2 categories, you have to use a chi-square test. You have to because you need a way to describe the whole pattern of differences you see. Okay, that's the point here. So there's a lot of words here. The value of our measured parameter could be bigger or smaller than expected, right? So a z and t can be either positive or negative. This can only, a chi-squared can only be positive because it's the sum of squares. So sometimes we're not just looking at one number, but a pattern of 2 or more numbers, you know. And then we want some way to see whether the whole pattern differs by more than typical random variation from what you'd expect under some null hypothesis. Okay? So that's what I say here. We want some way of saying whether the whole list of differences are big or not. So we could focus on just one part of the list. Like if you wanted to, you could collapse these two into zeros and just say the percent of ones and then get back to this situation. But sometimes we want to look at the whole pattern. And then we have to use the chi-square test. All right? So how many degrees of freedom do we have in this chi-square test? Remember, we're going to have a different chi-square curve for depending on the number of categories here. All right? So basically, what did we say here? The chi-squared is the sum of z-scores. Yeah, it's really a measure of how far Our sample landed away from our null expectations, expressed in a sort of normalized units we use for z-scores, but squared, right? So that's what I said there. And you're going to get a different chi-square distribution depending on how many independent squares, degrees of freedom, we added up. Right here, I said if your model specifies the percent composition of each, but they have to add up to 100%. These are mutually exclusive categories always. So they have to add up to 100%. So if you know n minus one of them, like if you know two of them, the third one's determined. So you have your degrees of freedom. So the degrees of freedom right here is how many independent squares you add up, how many independent categories you have. So the degrees of freedom is equal to the number of categories minus 1. Okay? So a chi-squared with 1 degree of freedom is just a box that's a 1 and a 0. Just has 2 categories. We could code it like this. So that's what it would look like. So that's going to be the same as, that is the same as a z test. A chi-square test with 1 degree of freedom is the same as a 1-sample z test. But it's going to be two-sided because we can't distinguish between positive and negative. So it's going to be the same as a two-tailed. You'll get the same p-value. Okay? And your actual statistic would be just z squared. You can test that out if you want. All right, so with 2 categories, we can do either one. We can do a 1-sample z-test, which is what most people do, or a chi-squared, goodness of fit. Okay, so that's the idea. And now let's just go ahead and do the test, and you'll see what I mean. All right, so now let's just write it's the observed okay, so a die is rolled 6 times with the following results. So these aren't really values. That's a bad term for it. These are categories. So we have 6 categories, right? And this is what we observe. So basically our box looks like this. This is our null box. And we're trying to see whether the die is fair. So we have 6 categories. These, they could be expressed as A, B, C, D. It's just which way the die lands. There's 6 possibilities. That's where the 1 comes from, 2 spots, 3 spots, 4 spots, but it could just as easily be A, B, C, D, E, and F. Those numbers just indicate how many are in each category, 5 and 6. All right, so this is always observed counts. Observed right here. This is going to always be given to you, and this is your observed data in counts. Observed frequency, it's called, or counts. And this is your expected frequency or expected counts. Counting how many times, count how many times it fell in each one. And so there's 6 categories. So you could have 6 tickets in the box. And what's the idea? So you want to do a chi-square test to determine whether the die is fair. And the null is always what? That the die is fair, that our observed counts, what we observe, fits our model. So the die is fair. It's like a random draw from here. We're not going to get exactly equal amounts of each one of these, but what we observe, we're going to do a test and see that what we observe is within chance variation. So the observed data fits the model. Good. Goodness of fit. Fits the model well or good. It just fits, you know. And the alternative, by the way, the alternative, sometimes you put a little 1 here. You'll see that, but we've been using an A. The alternative is what? That the die is not fair. That the observed data does not fit the model. Okay? That's the idea. That these differences that we observe, when we actually do the test, we're going to observe differences that are going to show bias. Right? So now we have to think, okay, so we're going to roll the die how many times? There's your n, 60 times. So we're going to draw from here. We're going to draw randomly n equals 60 tickets. And this is like a gambling game. It's with, of course, there's only 6 tickets in here, right? But we want to keep the odds the same every time. So it's with replacement. All right. And then what would we expect to see? What do you think we'd expect to see? We roll it 60 times. And since this box says that each one of these is equally likely, what do you think you'd expect to get for each one? What do you think? You'd expect, your expected is going to be equal to, each one's equally likely, and there's 6 categories, so you expect 10 for each category. So that's what our expected is. Okay, and now remember what we're trying to do is, okay, we expect this, and what did we get? Well, it looks like we got too many 3s. We got 7 extra 3s. We didn't get many, we got 6 too few, 10s, but how can we assess all of them? Like if we just wanted to say, hey, is it favored toward 3, we'd just have a 0, 1 box. We'd say, okay, if you got a 3, it'd be 1. If anything else would be 0, and we'd see if that 17 is too much. All right? But when we want to assess the whole pattern, then we have to look at these, our observed minus expected, not just for one of them, but for all of them. And if we do that, 4 minus 10, that's negative 6. 6 minus 10 is negative 4. Here you have those 7 too many 3s. Here we have 6 too many 4s. And here we have negative 2. And here we have negative 1. And if you add them all up, they sum to 0. You can see that, right? Negative 10 plus 30. Here you have 3 extra. Minus 2 is 1. And the last one is 1 minus 1, right? Here, and so they have to sum to 0. And what I just did was an illustration of how there's only really 5 independent categories, right? If you sum them, take any 5 of them, like here you sum these and you get positive 1, we know sum these, you get positive 1, you know the next one has to be negative 1 to sum to 0. And you can do that with any 5. So you have 5 degrees of freedom. That's how you can think of it. You can think of 5 of these categories are free to vary, degrees of freedom, but the last one is determined. So you have n minus 1 categories, degrees of freedom. So let's write that down. And let's also write down this chi-square statistics. You have this observed minus the expected. These differences. You can't just add them up because you're always going to get 0. This should remind you of something like what we did with standard deviations, right? You can't just add up these differences because you'll always get 0. So we need to square them to get rid of the signs. It's always going to happen when you have more than 2 differences. All right, so now we're going to say the degrees of freedom is equal to the number of categories, the number of independent categories. So that's the number of categories minus 1. Okay? And as you notice, these categories are always mutually exclusive. You can't get both a 1 and a 2. If you're in one category, you're not in the other. Okay, so that is equal to 6 minus 1, which is 5. That's our degrees of freedom. And now, what's our chi-square statistic? Our chi-square statistic is equal to what? These differences, but you have to square them, so it's the sum. That's the sum from, for each of the 6 categories. We're going to sum the 6 categories of the observed count the observed frequency minus the expected. These, we can't just, and we're going to divide by, okay, the observed minus the expected squared. But we're going to divide each one by its expected. Because here they're all the same. But sometimes you might just have a tiny little category, and so you're going to get a small difference from it. So we have to normalize these, basically. That's what we're doing relative to what we expect. You know, if you have a big difference, you have to normalize it according, because, you know, if you expect a whole lot, then you're going to get a bigger difference, more likely to. Okay, so that's what we do. We make them, so that's, we do that, and then let's do it. So here, let's square these each. So we get 36, 16, 49, another 36, a 4, and a 1. All right? Now, but we have to normalize them. We have to divide by their expected. So let's do that. So 36, well, they're all the same expected here. So it's 36 divided by 10, 16 divided by 10. You have to do all of these, right? 49 divided by 10, 36 divided by 10, 4 divided by 10, and 1 divided by 10. We do that, we get 142 divided by 10, which is 14.2, and that is our chi-square statistic. Now in this case, because we have a common denominator here, of course you could add them all up here and then divide by 10. But don't do that routinely, because if you don't have, in the next example, you're going to see we're not going to have the same expecteds. So I don't want you to get in the habit of that, but I'll just, I mean, certainly it would be easier to have done this, but only sum when you have a common denominator here, otherwise you can't. Only sum when the expecteds are all the same. All right, so this is our chi-square statistic. Then you could sum them all and divide by 10. All right, now that's our, so is that big or small? Well, you have to look at the chi-square distribution, and there's a different curve for each number of degrees of freedom. So let's look in the back of our book and see what the curve looks like, okay, and where that falls. How to do this, okay. So here's the chi-square. This one just happens to be the one for 5 degrees of freedom. So as you get more, see how it's asymmetrical a little bit? It's sort of symmetrical, but it has a long tail. As you get more and more categories, it's going to, the shape of it's going to resemble the normal curve, and with a middle, with the expected value, right at the degrees of freedom. So right away, you know 5 degrees of freedom, you'd expect 5. We got way more than 5. We got 4, so we're probably going to have significance. But let's see what the cutoff, so 5 degrees of freedom, you look here, and here it's going to give you the range of, it'd take too many pages to give you the p-values for every different chi-square stat. So here, what do we have? We have our chi-square stat is between, it's right here. It's 14. It's very close to 15, but it's 14.2. So it's between 1 and 5%. So if you were just given the table, you'd say it's between, it's bigger than this one. This one is 11.07 right here. So here is 5%. And ours is where? Way out here. So it's certainly less than 5%. This one just happens to be the one for 5 degrees of freedom. So it's convenient. So this right here is the cutoff. Like this is the critical value, right? The null cutoff for 5%. So ours is bigger than that. So certainly our p-value is less than 5%. It's between 1 and 5%. So let's just draw this curve so you can get a feel for it this first time. So we know that our p-value is between 5% and 1%. And our curve, we'll just do it this time because we'll give you a feel for it. Okay, why? No negative numbers, right? No negative numbers because they're squares. And, okay, 0, 5, 10, 15, and 20. And I said the mean, the expected value of the chi-square distribution is this when the null is true. When the null is true, like this is when always assuming the null is to be true, is 5 degrees of freedom. For 5 is its degrees of freedom. So if it was 10 degrees of freedom, it would be out here, etc. Okay, so now we're going to make it sort of looking like that. And then it goes down and keeps going forever, right? Okay, looks like that. All right, so that's the chi-squared degrees of freedom. And now we saw right here that the critical value is 11.07. That's the chi-square critical value. It is 5%. What does that mean? That from here on in, out, this tail is 5%. We got 14.2, so it's more extreme. So here's our 14.2. And we know it's between 1%, because 15 was 1%, I think. We can find out exactly what that p-value is. Why don't we find out what it is, what this area is, and you can just, this might be a good time to look at what chi-square curves look like. So let's go to our computer here and just take a look at the chi-square distribution. So where do we get that? Let's go to our p-value calculators, and now we're going to look at the chi-square. So we have degrees of freedom is 5, and we got our chi-square of 14.2. So we said we think it's close to 1, a little bit bigger, and let's see what it is. Notice there's only a right-hand tail. There's a left-hand tail too. So we have 1.439. That is our probability. It looks like this. Okay. Now the cutoff for 5%, if you want to see what you need to get to achieve 5% significance, is what? That's 11.07. That's right here. What's the cutoff for 1%? You could do that, and then you would compute that's 15. We have in between there, and we said, now I've already forgotten it, 14.2. What was it? It was 1.4%. That's as a decimal. Okay, now watch what happens. Look, if you only had 1 degree of freedom. If you only had 1 degree of freedom, this is going to be at, look what it's here, compute the p-value. See how that looks with only 1 degree of freedom? It is exactly the z squared here. You know, all the z's between 0 and 1 are going to get smaller when you square them, right? A half times a half, like the negative 1/2 and the positive 1/2, that's a quarter. So everything that's a fraction is going to, all the 68% of the data that's a fraction is going to go way up here and get smaller and smaller. So it's a very asymmetrical curve here, okay? And it keeps going out. And this look is a very, remember we'd expect a chi-square of about 1 equal to its degrees of freedom. And so then if we compute the p-value, you don't get 50%, but you get the this isn't asymmetrical, so you don't get the median, so it doesn't divide it in half, but this is the expected value. All right, and look what happens if you have 100 degrees of freedom. Now it's going to start looking like the normal curve, and we'd expect a chi-square of 100, and what would we get here? Now it's going to be very symmetrical, and this cutoff, the area of this, is going to be close to 50%. Okay, so that's the idea with the chi-square distribution. You're going to see it over and over and over again, because what it is basically the sum of z-squares. So if you have categorical data, you'll see it, and because of the central limit theorem, you know, z is a very good, the sampling distributions of averages and percents become normal. So if you have multivariate data, this is multinomial, the binomial multinomial. If you have multivariate data, which we're going to have with multiple regression, you are going to see the chi-square distribution over and over again. So it's just like you see the z distribution. Okay, so that's the idea. Now let's move on Any questions so far? I'm excited about the chi-square. I like the chi-square distribution. So I'm showing it to you and explaining it, and you're going to see it so much. So, all right. So now let's do an example. This is really exactly the same thing. I don't even know why I'm going to do this example. The only reason would be because there are different percents. So let's just go through this one quickly. So what does it say? A small town has 50% Christians, 30% Jewish, 20% Muslim children. 100 children were chosen to participate in a community project. So this is what we'd expect because that's what the town has. And then we observed, of the 100, we observed these numbers. Could this have been a random sample? You know, you might want to do this with, you know, a jury, like it's supposed to be representative of your peers, so you could see what the town composition of the town is, and then you could do a chi-square statistic to see if the jury panel was chosen. You know, the 100 people they randomly choose for the jury before they do all those questioning of them. You could see if that was a fair representation, and that is done. That's a good test to see if some population that you've randomly chosen is representative. The percent composition really does mirror the percent composition of the whole town when you have more than two categories, like blacks, whites, Hispanics. If we wanted to see in our class whether this is representative of the university or something. We're not a random sample, but if we wanted to see whether, if we were a random sample. Okay? So now let's look at this box. So we have in the town, and the box is the whole population. This is your null box. It's like a gambling game, so you make it for a single play. Here, you always make the box for the whole population, right? So the null box, and that's the whole it's the population, and here it's for a single play, like we always do. So this is really, the logic is exactly the same as our hypothesis test. We just have a squared statistic. That's the only difference. So in our population, we have Christians, Jewish, and Muslim, and it's the 50%, 30%, and 20%. So we have three categories, and we have, like, let's say the town had thousands of people. So we're going to have thousands of tickets, right? But we have three categories. And now we're going to sample, okay, so what's our null? Our null is what? The children were what? Randomly chosen from this box. You need some kind of, like, our observed data fits a random model. You need some kind of randomness in there, otherwise you can't do any significance test. So that's what you have to be able to translate it. For these two cases, we can. Children randomly chosen. Okay, and then you can say that our observed categories, or our observed counts, data counts, whatever, that's what our observed data is, fits our model. And then the null is what? No, the children were not randomly chosen. And we're going to show that the observed data does not fit. Does not fit the model. It's going to be too far out on the tail. It's going to be too extreme. That's what we showed before. We have to reject the null here. We didn't finish our example here, did we? So this p-value was actually 1.4%. So our conclusion is between on table, but we got this from the computer. So we got this from the calculator, p-value calculator. So our conclusion is what? Let's put our conclusion up somewhere. So what is our conclusion? When you have such a little p-value, p is not at the 5% level, p is not less than that significance level. Let's say we have the 5% cutoff, p is less than 5%. What am I talking about? P is tiny. P is less than 5%. So what do? We reject the null. P is equal to 1.4%. So we reject the null. Very strong evidence that the die is what? Unfair. Do you get it? Sorry about that. P is less. So we reject the null. It's way out here. So we're going to say, looks like the alternative true. It's just so unlikely. That's what we say. All right, now let's go back to this one. Does everybody understand that? Okay, so now we're back here, and what are we going to do? So we don't have this table, so let's make one. So let's just do this. So first of all, what are we doing here? We have 3 categories. What's our n? How many times are we randomly drawing from this box? How many in our sample? Where is it? Right there, 100, right? And by the way, this is going to be what? With or without replacement? Are we going to put the children back? No. So it's without replacement. That doesn't, if you wanted to be a stickler, you could use a correction factor, but 100 is such a small percentage, we're not bothering with it. I just want you to get the logic of it. That's why I'm saying this. It's not going to affect, this is not affecting your calculations with or without it's not. I just want you to understand the logic and really picture what we're doing. That's why I'm focusing on it. All right, so now what are we going to do? So we have the Christian, the Jewish, and the Muslim. So let's just make our own chart here. All right, so observed. This is always given to you. And where is our observed? What did we get? We got 50, 40, and 10, right? Okay, 50, 40, and 10, and it sums to a total of 100. So now our expected also has to sum to 100. And what is our expected? Well, we want, it's 50% of our sample, so it's 0.5 of 100. It's easy. So it's 50% of 100. So it's just going to be 50, 30, and 20. If this wasn't 100, of course, if this was 200, for example, then it would be double these. But since it's 100, it's the same as the percents here. Okay, so 30% of 100 and 20% of 100. I'm writing this just so you don't always think, just because you see those, you're going to put that, right? It has to sum to this. If we had 200 observations, it would have to sum to 200, obviously. Okay, so we've got that. And then what's our differences? Our observed minus our expected. Well, here it's 0. We got exactly the number of Christians we expected. Here it's the observed. We got 10 extra Jewish kids and negative 10 fewer Muslims than we expected. Okay? So that's what we have. And this has to sum to 0. Now, that's why we can't just average these. We have to square them. So we get the observed minus the expected, and we're going to square these. So we get 0, 100, and 100. And don't sum them here because they have different denominators. They have 50, 30, and 20. So don't sum. So don't sum these because the expecteds are different. Okay, so now what we really want, this chi-square statistic, is the sum of the observed minus the expecteds squared divided by each one's expected. So now we have 0 divided by 50. And here we have 100 divided by 30. And here we have 100 divided by 20. So that's 0. That's 3 1/3. And that is 5. So our chi-square statistic is that. All right, that's our chi-squared statistic. I'll just write this so you remember it. The observed, actually this is what I'm going to be giving you though. The observed minus the expected squared. This is just what you're going to see over the expected. Just because it's not exactly like all the other ones. All other ones are observed minus expected over standard error. So that's the only reason I'm giving it to you. You should know it after a while, but since it's just the week before the exam and you're learning a somewhat new formula, this will just be on your exam. Okay, so that's it. And then we get 8 1/3. That's what that should say, 1/3. So that's 8 1/3. And what's our degrees of freedom here? What is our degrees of freedom? You know, what is it? 3 minus 1, which is 2. So right away, you'd expect 2. If the null was true, your expected value for the chi-square statistic, the mean of the chi-square district would be about 2, and you get a lot bigger. So it looks like there's significance, but we have to look it up. So let's do, because you're not used to this, so we go and we look for 2 degrees of freedom. And you'll have this chart on your exam, this exact chart. So we look at the 2 degrees of freedom, and what are we looking for? 8 and 1/3. So it's right here again between 1% and 5%. So if this is all you saw, you'd just say the P is between 1% and 5%. It's in that range somewhere. Because it's 8 1/3. Okay? So we can write that down. So our p-value, looking at the chart, our p-value is between 1% and 5%. So we reject the null. It's not highly significant, but it's significant. If we're going to use our usual conventional cutoffs, we reject the null at the significance level. That's our significance level. If we use that, reject the null at alpha equals 5%. Often written when you do the alpha as 0.05. Okay? That's our significance level. So we reject it. Okay? Does that make sense? And conclude, so we what? And conclude what? Because our p is less than 5%, that there is strong evidence that the kids were not randomly chosen. Can you read that? Randomly chosen. That, oh gosh, that's, you can't even see it. The kids were not, that looks horrible, were not randomly chosen. I need to leave more space in this notebook the way I write, but then you'd have too many pages to carry around. You probably do a better job at your seats of filling it in. All right, so let's just go on. Any questions on the chi-square goodness of fit? We are done with that. You can do your homework easily on that. Now, moving on to the next test. All right. Now, what are we doing next? All right. So we did the goodness of fit. Okay, we examined whether the data we observed fit a particular model when the model had more than 2 categories. We really should say 2 or more, because we can still do it with 2. But the chi-square, we didn't really do an example of it, but you could. All right, now let's see. In general, when you're comparing the district, so we had 1 variable, 2 or more categories. Like our variable was religion. That was one variable with 3 categories, okay? But now, let's say we have 2 variables, and each with 2 or more categories. And we want to compare them not to some model, but to each other to see if they're the same. So let's say we had we had variable like gender. So you have males and females, that would have 2 categories. And then we have, let's say, yes, no, or maybe. So we want to compare their responses to some question. Like the last one we asked was what? It's Valentine's Day, so did you ever fall in love at first sight? You might answer yes, no, or you might be unsure. You might think, was that love at first sight or not? So you'd have 3 categories. Last time we did a 2-sample z-test, right, for that, but if you have 3 categories, you can't code them that way, so you have to do a chi-square independence test. And the idea is whether you fall in love at first sight, whether you answer yes, no, or maybe to some question, that's one variable, whether your love feelings, and the other variable is your gender, whether they're independent of each other, whether your response to that question depends or not on whether you're male or female. All right, we'll see when you have more than 2 categories. So in the simple case of 2 groups compared along 2 categories, the chi-square independence is the same. All right, if you just have one variable with more than 2 categories, let's summarize this. All right, if you just have one variable with, all right, I can say the same thing as I did here. In the simple case of 2 groups compared along 2 categories, the chi-square independence test is the same as the 2-sample z-test. We're going to see that in a minute. And we just looked at, in the simple case of one variable, just a 0, 1 box, with just two categories, the chi-square goodness of fit test is the same as our one sample z-test. But it has to be two-tailed because it can't distinguish between positives and negatives. Is the same as the 2-sample z-test, two-tailed. So let's just summarize this. All right, so let's just make an easy way to summarize this. All right, so what's the difference here? So we looked at the chi-square goodness of fit test. And this was our null box. We had categories, right? Multiple categories. More categories, right? More than 2. And you have one variable. We have just one box here, one variable. We're just comparing one thing like religion. And we have 2 or more categories. And our null is what? Our null is that our observed data, our counts and our observed data fits the expected model. Observed minus expected is not too big. All right, that there's nothing weird going on. These differences aren't very big. And then the degrees of freedom are the number of independent categories. So it's the number of categories minus 1. Because once we get the counts on n minus 1 of them, the last one's determined. So it's a good way to understand the degrees of freedom here. Now, what do I say here? In the simple case of one variable, so in the simple case of just one variable with 2 categories, then we just have 2 categories, and we can put the ones in zeros. So we can actually get a number here, a percentage, rather than summing up a whole bunch of differences. We can just say this, whatever percent of ones we have compared to our expected, that difference over a standard error for the over the standard error for the percent, this percent versus what we'd expect to see over the standard error, or we could do a count. We could do the standard error of the sum. Right? If we were counting up the number of heads, you could do that too. So you can do either a z or a chi-square. You can do either one. That says either. All right, now what about this independence test? What do we have now here? So the chi-square test for independence. Now we're going to have have 2 variables. Like gender would be one variable. You could even do male, female, and trans. You could have 3 categories there. And then you could say answer to some question, and it doesn't have to be yes or no. It could be yes, no, maybe. It could be, more than just 2 categories. All right, 2 variables, each with 2 or more categories. Okay, then what is our null? Our null is that the two variables are independent. That knowing one doesn't give you, knowing what gender somebody is doesn't give you any more clue about how they're going to answer the question than not knowing their gender. Okay, and then what are the degrees of freedom? Again, you have two variables, so the degrees of freedom are, here it was the number of categories minus 1. Here it's going to be the number of categories, again, minus 1 for the first variable, times the number of, that's number, hashtag number of categories minus 1 for the second variable. Okay, so in the simple case, would look like what? It would just be like a two-sample z-test. You'd have two categories, and two categories, so you could code them as ones and zeros, like that. Okay? And so now you can do either a z, two-sample z, or a chi-squared. And for all of these, so this would be a one sample. And it has to be two-sided, because chi-square is always positive. Two sample, and this is two-sided. Okay, so that's the big picture here, and that's the idea. Let's do an example, and you'll see how this works. Any questions so far? Okay. So this is a real study published in the Journal of Medicine that investigated the relationship between tattoos and hepatitis C. It was prompted, I remember, by an actress, Pamela Anderson, the one who was in a very popular TV show at the time. Probably never heard of her, but anyway, she got hepatitis C, and she claimed she got it from, and other celebrities too, from tattoos instead of other. You know, hepatitis C you could also get from drug use, dirty needles, and other stuff. But she said she got it from tattoos, so they wanted to see whether that was really, how likely that would be. So they investigated this to see how safe they were, whether they were causing hepatitis C. So they looked at 626 patients undergoing medical evaluations at a Dallas spinal clinic for reasons unrelated to hepatitis. So it was just, they said this, they assumed it was like a random sample, okay? Because it's not people weren't very, it was representative of the whole population. It wasn't people, drug users, or some other reason why they would get hepatitis C. So they just asked them, they were in there for spinal, because they had problems with their back. Okay, and they examined, and also the thing was they were naked under a lot of imaging, so they got good images of whether they had tattoos or not. So they had this huge data set where they could see whether they had tattoos or not, and they did extensive questionnaires about, asking them a lot of blood tests so they could see if they had hepatitis C. So, and then they just questioned where they got their tattoos. So here's the data, right? And so these are the observed frequency, and these are the counts, right? Frequencies are counts. They mean the same thing. All right, so now we look at this. This is what we got. And the null hypothesis was what? That whether or not you get hepatitis C right here, like whether 47 people had hep C, 570 not. Whether or not you do has nothing to do, this is not predictive of whether or not you do. It has nothing to do with whether you have a tattoo or not and where you got it from. All right? And the alternative hypothesis is no, that it does depend on this. Okay, so how are we going to figure the expected? We're given this. This is what you're given. And how do you think you figure these expecteds? Well, you figure them under the null hypothesis. So the null hypothesis says the probability of getting these hepatitis C or not has nothing to do with where you got it from. That 47, you figure under the null to be true. You see that 47 out of 626 people got hepatitis C, right? So you can think the probability of hepatitis C among these people is 47 out of 626. Overall, here's the overall total. And out of that overall total, 47 out of the 626, which is 7.5%. So this is equal to 0.075, which is 7.5%. That says 0.075, okay? And then if 7.5, this is 92, 579 out of 626 don't have it, so that's 92.5%. So we can write that. So the probability of no hep C is 579 out of 626, which is what? 0.925 or 92.5%. So now that you know that, you'd expect, if they're independent, knowing whether somebody, okay, so you look at these people here, 52 of them, it was these are the totals here, right? These are your totals. These are your totals. So you'd expect, if it didn't matter where you got your tattoo from, or if you have a tattoo at all, you'd expect within each category you would see 7.5%, right? Because that's what we had in the total. This is 7.5%, this is 90. So you'd expect 7.5% of these people. So of the 52 would have hepatitis C, right? And that is 3.9. And you'd expect 7.5% of the 61. And here you'd expect 7.5% of the 513. So that's how you would get all your expecteds. And here, since 92.5% total, right here, don't have hepatitis C, you'd expect within each group that would be the same percentage. So this would be 0.925 times the 52. And that turns out to be 48.1. They have to add up to 52. So you could have just gotten that one from that one, right? And once you get, does that make sense? All right. So now another way, and we could fill it in there, but a shorthand way of doing this, some people like this better, is this. Why is that the same thing? That you could figure each one by doing this. Look, this 47 is the row total. This 626 is that. So what are we doing here? This 0.075 comes from 47 divided by 626, right? That's for these. And then we're taking that and multiplying it by this. So it's the same thing as your row total times the column total over the overall total. It's the same way. It's just easier to remember it. So it's really exactly the same thing. You know, here, this translates as 47 over 626. So there you have the row total. And the denominator for all of them is 626. And then you're just multiplying it by here. You have 61, and that corresponds to that. Okay? So if you just wanted to do it for all of them, that's how you would do it. So here, all of them are over 626, but now you have the 92.5, so it's column total, it's row total. That right there is the 92.5%, and now you're multiplying it by its column total. So that's another way to do it. All right, and this was 4.6. And once you have these totals here, once you have two of them, right? Once you have this one, two independent ones, right? Once you have two independent categories, you could figure out all the rest of them. Because this one plus this one has to add up to that. This one plus this one. So you could figure out all the rest of them. These two plus this one has to add up to that. I'll show you what they are. So it's a good way to check. Whoops. You know, this one has to be what? 56.4. And you could check that it is. And 47. These two have to add up. These three have to add up, etc. Okay. So basically what we're doing here is we're saying 92.5% of the 61. And here we're doing 92.5% of the 513. That's how we're doing it. Any questions on that? So now you see that we really only have if you pick two independent categories here, the rest are determined. And notice that our degrees of freedom, remember, the degrees of freedom, let's see if it checks out. We know it's 2, and let's just write down here. The degrees of freedom is going to be equal to the number of categories for variable 1 times the number of categories for variable 2. And let's see if we get to. There's two categories. We could say, well, it doesn't matter. So we have 2 minus 1 times 3 minus 1. This is times, not plus, times. And what is that equal to? That's 1 times 2. And it checks with what we saw. All right. So now we're going to have to, what are we going to have to do? We're going to have to do the statistic. It's going to take us a while. Oh, we have to do all this. All right, so it's the observed frequency minus the expected frequency. All right, let's just do it and get it. So you're not going to have to do such a big, long calculation on your homework, or certainly not on your exam. I'll give you some of these, but basically what are we going to do? So we're going to say we have to go for, let's go across the row here. We have 17 minus 3.9. All right, so we'll say 17 minus 3.9 squared over the expected is 3.9. Now we'll do the next one. What is it? 8 minus 4.6. That's a big difference, 17 minus 3.9. So this is 8 minus what? 4.6. 8 minus 4.6 squared over 4.6. And the next one is what? 22 minus 38.5. So a lot of calculations. I promise you're not going to do this many on the exam. I'll give you most of them, just have you fill in 1 or maybe 2. All right, the next one is what? 35 minus 40. 8.1 squared over 48.1 plus, oh, I forget what that was, 53 minus 56.4 squared over 56.4. And the last one is 491 minus 474.5 squared over 474.5. Oh, too many calculations. Anyway, I got 58. So, and we already saw this was our degrees of freedom. So we said this was equal to 2 minus 1 times 3 minus 1, which is 2. And should we reject the null? You don't even have to do a test. Remember, should we reject the null? We'd expect the mean to be about 2, and we have 58. This is astronomically. Yes, our p is tiny. It's just going to be way, way, way out on the tail. So p is way, way, way less than 1%. You could check it here, and I'm sure it is. You could look. How many degrees of freedom? We have 2 degrees of freedom. 13.82 would give us a value of 0.1%. So our P has to be way less than 0.1%. Our P is way less than 0.1%. Way less than 0.1%. So we have enormous significance. So what does that mean? I mean, in this case, we know that something was going on with the tattoos. Okay? So it was a very important study. So we reject the null. There's overwhelming evidence that hep C depends on tattoo status. But what do I mean by that? Is it causal? No, we haven't proved that it's causal. We just see an association. Does this, we didn't randomly assign the people to the different categories. You didn't randomly have them get tattoos at different places. Does this mean they were just randomly selected from a large population? So we can extrapolate to a large population, but we can't infer causality. Does this mean that getting a tattoo or something about a tattoo causes hep C? It could be, but no, maybe. But all we see is an association, but we don't know. There could be a confounder, right? This is just observational data. This is observational data. The people we're assuming they're randomly selected. That's completely different than randomly assigned. So we could, so what does it mean? There could be a confounder. You have the tattoo. We're wondering if it's somehow where you get it from causes the hep C. But there could be a confounder. Okay? There could be a confounder. It might cause it if they're using dirty needles, or a confounder might be the people who get tattoos also do a lot of risky behavior that could lead to, has nothing to do with the tattoo. You understand? Okay. So this is just associative. These significance tests do not tell you causation. They just tell you whether we're likely to see this from chance. Unless it was randomly assigned to treat, unless it was a randomized experiment. This was just observational data. All right, now, and this shows how we could do this quickly. This shows how we could have done the two-sample Z test we did before as a chi-squared. Remember we had this, and we saw these percentages. All right? So now you have to change, to do chi-square, you always have to change percentages to counts. All right? So how would we do that? Same thing that we did on page 80 previously by a chi-square test. So we'd say, we have 500, we'd say 0.44 times 500 of the men is 220, right? And 0.36 times 500 of the women is what? 180. So altogether, 400 said yes, and 220, we can just say the no's have 280 here, and 180, 320 has to add up to 500, and this has to add up to 600. Okay, so that's what we observed. Now, what would we expect under the null? What would we expect? Well, there's a 50-50 split here. We know the totals are the same, right? The totals, whoops, they have to add up. The totals were given to us. So now, what would we expect? Well, wouldn't you expect if there's 50% of the men and 50% women, that 50-50 split here? Or what you could do is you could say, you could go 500, which is the row total, times the column total over the total total. But you could also see that's just 50% of the 400, and that's 200. So this is 200. And this has to be what? 300 and 300. So you'd expect this split if it was just due to the luck of the draw. You'd expect that if their answers to this question didn't depend on their sex, that we'd see the same. All right. So the people who said yes would be evenly split between males and females. All right, so then we do this chi-square stat. And what would you do? Here it's easier to do. We see, is this difference big or small? We have a difference of 20 here, 220 minus 200 squared over 200. So we just say 220 minus 200 squared over 200. And here you have 280 minus 300 squared. See, that's another 20. The differences are all going to be the same. We only have 1 degree of freedom here. That's going to be 20, but this is over 300. And this is what? This has to be 22. 20 as well. So this is plus right here. We're doing these two. It's going to be a difference of 20. They're all going to be 20. We only have 1 degree of freedom, right? 180 minus 200, so it'll be 20 squared over 200 plus 320 minus 300 squared over 300. So basically, what do we have? We have 400. We have 20 squared over that. So we have 6 2/3. All right, degrees of freedom. What are our degrees of freedom? Once you know one of them, it's 2 minus degrees of freedom is equal to 2 minus 1 times 2 minus 1, which is equal to 1. So when you have a chi-square test with 1 degree of freedom, it's exactly like a z. It's the sum of just 1 z squared. All right? So what did we get? The 2 sample, okay, so what we can look that up, and you get a p-value, I already did, of approximately 1%, which is exactly what we got before on page 80 when we did it. So if you look at page 80, we did it both as a 2 sample, we did it both here as a 2 sample z, in which case we got 1%. This is equivalent to a chi-square. As a 1 sample, we got 0.5. So it's a nice illustration of that. Now I lost my place right here. Okay, page. So the 2 sample z-test, it's the same. We got, okay, so I'll just write the p-value for the chi-squared for the chi-square independence test was 1%. And that is equal to the p-value for the 2 sample z-test. When it's 2-sided. That was 1%. 1-sided was just half of that. The 1-sided 2 sample z-test gave us what? P-value for the 1-sided is equal to just half of that. But for this, they were the same. That was the point. All right, I think in the last 5 minutes, just so you can do your homework, we can skip this because it's exactly like what we've been talking about. We can fill it in later, but basically just see page 80 because you'll get the same results. See page 80, you'll get the same p-values as page 88. This is the 2 sample z, and that's what we just did. That's what I just showed you here. We can go over this more later, but I can fill it in online, but it's just what we just did. I want to get to this because we really only need 5 minutes for you to do your homework. So what's the point here? These significance tests, what do they tell you? People make a big deal about significance tests, but statistical significance is very, very different than practical significance. Significance tests only tell you, this is the most, whether a difference is likely to be due to chance, not whether a difference is important. Why? Because any difference with a large enough sample will become significant. If you have the entire population, all it means is it's not likely to due to chance. Because we can make our standard errors really, really small. All right, so suppose investigators wanted to compare IQ scores of men and women. They take a random sample of a huge sample, all right? And the men average 100 on the IQ test with a standard deviation of 20, and let's say the women average 1 point higher. They do a 2-sample z-test and conclude the difference is highly significant. But who would care about a 1-point difference? I mean, it's significant, but it's meaningless in terms of what we care about. If you know about the IQ test, it's just so tiny that it doesn't mean much, okay? So whether something's statistically significant is very different than whether you care about it, because any difference, no matter how minuscule, will become statistically significant if you have giant sample sizes. That doesn't mean it's a difference we would care about at all. Okay, so that's important. And here, this is a huge important thing. And it says with enough significance, with enough tests, significance results will appear by chance. So if you run 100 tests, you can expect 5 to result in statistically significant results even if the null is true. Why? Because that's the meaning of the null. That's what 5% means. It means that, okay, you assume null. You assume null is true. So 5% significance, what does that mean? It means that when the null is true, these 5% of the time you're going to be wrong. Just by it's not going to, you're going to reject the null and be wrong. This is going to occur just by chance. So you don't want to, this is very much the same as data cheating, data snooping, if you don't report how many tests you ran. So if you run 100 tests, you can expect. So you can't just pick out those 5 tests and say, hey, I've got significance. I'm going to show people have ESP, or I'm going to show this, or I'm going to show that. You have to say how many tests you ran. So beware of when many tests are run, or should have been run. So people will hide. So investigators must report how many tests were done before they found significance, or how many other people were doing tests. They can't just say, oh, we saw this. For example, I'll just do a quick example. If I asked 100 people, like if I picked a number between 1 and 20, okay? So there's 20 possibilities. There's 100 people in this room. Well, probably just by the luck of the draw, 5 of them are going to guess the number, because there's a, 1 out of 20 is 5%. So just 5 of them are going to guess. I can't say those 5 people read my mind, right? Because I ran a whole bunch of tests. So you can't do that. You have to do it again and again, show, and that was exactly what happened with the ESP example or something like that. They cheated by, there are tremendous numbers of people are trying to prove there's ESP, and one of them, just by the luck of the draw, might get significant results. Well, if you ignore all the other ones, that's the deal, okay? So that's enough for you to do your homework on it, okay? That's the key idea. And I'll post these filled in notes that I skipped. So I'll post this page. So I'll post this page. So fill in on your own. Fill in for bonus points. And I'll post this one and this one, because I did not. This one I can just post because it's, do I really have much to say here? Okay, I'll say fill in for bonus points. And I'll fill it in more nicely. Okay, and I'll post them.